Okay, so where we ended was when we were reading was complex multiplication, and then we worked some problems on the commutativity, associativity of complex numbers. We also talked about the fact with the identities, the additive inverse, the multiplicative inverse for non-zero complex numbers. Oh, we did show the distributive property. So we've essentially are establishing that complex numbers are a field. It says here the properties above are proved using the familiar properties of real numbers and the definitions of complex addition and multiplication. True, we saw that in the videos that's what I used. The next example shows how commutativity of complex multiplication is proved. Proofs of the other properties above are left as exercises. Oh, we did this also. We went over this proof for commutativity of multiplication. All right, next we define the additive and multiplicative inverse of complex numbers and then use those inverses to define subtraction and division operations with complex numbers. Let's see, here you have the additive inverse. So, and the fact that subtraction turns to adding the negative. Multiplying, so 1 over alpha is the multiplicative inverse. So we have to show that there is a multiplicative inverse. That'll probably be in the problem set, that it actually exists. Division by alpha is defined by multiplying by 1 over alpha. Okay, yeah, so all that makes sense. And all that copies what is true for real numbers, which are a subset of the complex numbers, by taking the imaginary part equal to 0. So if you take a plus bi with b equal to 0, then you have the real numbers. So you would hope that the bigger set, the complex numbers, would inherit the properties of the real numbers, so that we can conveniently make definitions and prove theorems that apply to both real and complex numbers. We adopt the following notation. All right, here it goes. He's using the letter F. So what do you suppose F stands for? Yes, that's right, field. So throughout this book, F stands for either R or C. So F for field, because the real numbers and the complex numbers are pretty much your classic ideas of examples of a field. And you see he says it here in the, I don't know, you call this a blurb or whatever. The letter F is used because R and C are examples of what are called fields. All right, thus, if we prove a theorem involving F, we will know that it holds when F is replaced with R and when F is replaced with C. So yes, if we use the properties of field to prove things, then we know not only does that it holds for C and R, I think, what is it, Z sub P, the integers mod P, aren't those finite fields if I remember correctly? Yeah, so we can have all kinds of fields. The elements of F are called scalars. The word scalar, which is just a fancy word for number, is often used when we want to emphasize that an object is a number, as opposed to a vector. Vectors will be defined soon. For alpha in F, our field, and m a positive integer, we define alpha to the m to denote the product of alpha with itself m times. So that's the way you do it for real numbers, is raising to a power is how many times you multiply something by itself, whether he's using alpha, the Greek letter, or something else. This definition implies that alpha to the m to the nth power is alpha to the mn. And alpha times beta in parentheses to the mth power is alpha to the m times beta to the m. Those are what we do in real numbers as well. So it should be familiar to you. This is actually nothing new, except you're thinking of alpha and beta as being in a field F, which are in this case including the complex numbers and the real numbers, but actually include a lot of other things if he just uses the properties of fields. All right, for all alpha and beta and F and all positive integers m and n. Lists. Before defining r to the n and c to the n, we look at two important examples, r squared and r cubed. The set r squared, which you can think of as a plane, is a set of all ordered pairs of real numbers. R squared is the set of all ordered pairs x, y, such that x and y are elements of the real numbers. So in other words, your x and your y coordinates come from the real numbers. They're r squared. It's an r squared. The set r cubed, which you can think of as ordinary space, is a set of all ordered triples of real numbers. That's the set of all ordered pairs x, y, z, such that x, y, and z are real numbers, are elements of the real numbers. Okay, so you would be familiar with that from analytic geometry and multivariable calculus. That subject is where you familiarize yourself with r cubed. To generalize r squared and r cubed to higher dimensions, we first need to discuss the concept of lists. So that's probably one good reason for you to have gotten through multivariable calculus, as it provides examples in r cubed for you. So you can attach with analytic geometry a geometric visualization of some of these things. So, all right, so list and length definition. Suppose n is a non-negative integer. A list of length n is an ordered collection of n elements, which might be numbers, other lists, or more abstract objects. Two lists are equal if and only if they have the same length and the same elements in the same order. All right, so n is going to be a non-negative integer. The length of your list is how many elements it has in it. Two lists are equal if they have the same length and the same elements in the same order. So order matters. So lists are often written as elements separated by commas and surrounded by parentheses. Notice it's not brackets. It is parentheses right here. I think we're safe to use a highlight here. Okay, thus a list of length 2 is an ordered pair that might be written as parentheses a comma b. So the order matters. A list of length 3 is an ordered, there's that word ordered again. Okay. So triple that might be written as XYZ. A list of length n might look like this. Z1 ... through Z sub n. So this is generalizing r squared and r cubed to r to the n, essentially, or c to the n. Z is usually used for complex numbers. Sometimes we will use the word list without specifying its length. Remember, however, that by definition, each list has a finite length that is a non-negative integer. Thus, an object that looks like x1, x2, ... which might be said to have infinite length, is not a list. So here, by definition, each list has a finite length. Okay, so we definitely want to remember that. A list of length 0 looks like this. Parentheses that's like the empty set. So this gives you a way to think of the empty set, by the way. Well, no, because this is an empty list. Sorry about that. Lists are not sets. Keep that in mind. We consider such an object to be a list so that some of our theorems will not have trivial exceptions. Lists differ from finite sets. You see, that's what I just said, is that, we should highlight that. Lists differ from finite sets. So that's something you need to remember, that they're not the same. In two ways. In lists, order matters and repetitions have meaning. In sets, order and repetitions are irrelevant. Okay, so his example, lists versus sets. 3, 5 and 5, 3 are not the same thing. But the sets 3, 5 and 5, 3 are considered the same thing. Because 3 and 5 are the same elements of the sets. But the elements in order are different, so the lists are different. The list 4, 4 and the list 4, 4, 4 are not equal. Their order and length, and they have to match. They do not have the same length. Although the sets 4, 4 and 4, 4, 4 are both equal to the set 4. F to the n. I'm going to stop soon. To define the higher dimensional analogs of r squared and r cubed, this is kind of what we've been leading up to, where f to the n is probably going to be a list of length n, right? We will simply replace r with f, which equals r or c, and replaces the 2 or 3 with an arbitrary positive integer. So the notation n, fix a positive integer n for the rest of this chapter. Definition, f to the n, coordinate. F to the n is the set of all lists of length n of elements of f. F to the n equals x1 ... x sub n, where x sub k is an element of f for k equals 1 to n. For x1 ... x sub n as an element of f to the n, so that's a list, right? And k in the set of numbers from 1 through n, we say that x sub k is the kth coordinate of the list x1 ... x sub n. If f equals r, that's the real numbers, and n is 2 or 3, then the definition above for f to the n agrees with our previous notions of r squared and r cubed. That means we can think of r squared and r cubed as examples of things we get when we work with f to the n. Example, c to the 4 is the set of all lists of 4 complex numbers. C to the 4 equals z1, z2, z3, z4 in a list, where z1, z2, z3, and z4 are elements of the complex numbers. Remember I told you a lot of times they use z for the complex numbers? And notice he often likes to use x in general, and I think also for real numbers. If n is greater than or equal to 4, we cannot visualize r to the n as a physical object. Well, similarly, C1 can be thought of as a plane. Oh yeah, because that's x plus yi. So the you have 2 coordinates. So yeah, so the complex numbers can be thought of as a plane. But for n greater than or equal to 2, the human brain cannot provide a full image of c to the n. Well, I hate putting limitations. Anyway, however, even if n is large, we can perform algebra. sometimes we mentally limit ourselves. Um, I guess I'm the optimist. That's why I read a book like this. Is my optimism says we can do it. The human brain cannot provide a full image of c to the n. Okay, whatever. However, even if n is large, can you prove that? However, even if n is large, we can perform algebraic manipulations in f to the n as easily as in r squared or r cubed. Okay, good. So we do visualize in this algebraically, but don't we think of everything in, yeah. So for example, addition in f to the n is defined as follows. Oh, he says read Flatland. Okay, so he admits, how the sphere that moves through Flatland. I read the book, and it's a small book. So Flatland, a romance of many dimensions. It is readable. It is probably worth a read, considering how short it is. By Edwin A. Abbott. For an amusing account of how r cubed would be perceived by creatures living in r squared. This novel, published in 1884, may help you imagine a physical space of 4 or more dimensions. I want to go on here, but I need to go and start my day. Thank you for listening.